Okay, good day. This is AP Calculus. I am Mr. McCully, and this is the presentation for section 8.7 LHopitals Rule. And this is the last one for the year, so let's get right to it. Okay, today we're going to recognize limits that produce an indeterminate form, and then we're going to apply a LHopitals Rule to evaluate those limits. All right, so what is an indeterminate form? A limit that produces 0 divided by 0 or infinity over infinity are both called indeterminate forms. Sometimes these indeterminate forms can be easily dealt with. For example, we have had a few indeterminate forms that have been previously covered with various other techniques, such as the dividing out technique. And so if we look at this one right here, this limit, the limit is x goes to 2 of x squared minus 4 over x minus 2. When I plug in 2 into this function, I get a 0 here, or get a 4 here. 4 minus 4 is 0, and I get a, when I plug in a 2 here, I get 2 minus 2. That's also 0. 0 over 0 is an indeterminate form. The way that we dealt with that, though, was we said that this thing was equal to the limit as x goes to 2, and what we did is we factored out, or factored the denominator, x minus 2, x plus 2, over x minus 2, and we saw that these two things canceled, these two factors canceled here, and so this limit was equal to the limit as x goes to 2 of just x plus 2, which is 4. And so we calculated a technique for finding the limit of an indeterminate form earlier. Another indeterminate form is something like this, where if I let x go to infinity, well, this is a polynomial function, and it's a quadratic function, so as x goes to infinity with a leading coefficient that's positive for both of these two, this top polynomial, 3x squared plus 4x, over the bottom polynomial, x squared plus 9, both of those will go to infinity as x goes to infinity. So we get infinity over infinity. But we had a rule that dealt with this particular indeterminate form. It said that if the degree of the numerator and the degree of the denominator were the same, then this limit was just the ratio of the leading coefficients. So we could say that this thing is just 3 over 1, which is 3. All right. So we have some other techniques to already deal with some of these indeterminate forms, but that's not always the case. As a for instance, let's talk about this limit here. This is an indeterminate form where those two or any of our previous methods for solving will not work. So as I let x go to 0, e to the 2x, well, if I plug in 0 for x, I'll get e to the 0, which is 1, minus 1 is 0, and then when I plug in 0 for x in the bottom, I get a 0. So this is still an indeterminate form that cannot be solved through the dividing out technique. But and I urge you to pause right here and just graph e to the 2x minus 1 over x. I don't have a graphing calculator that I can switch to on my computer. So like I said, take the time, pause here, and then graph that. And then when you come back, you will see that clearly this thing does have a limit at 0. You will see that the function goes towards a value from the left and from the right and points to the same value if you put it in correctly. So how can we actually calculate this limit when we get 0 over 0, which is clearly an indeterminate form? Well, L'Hopital's rule says that let f and g be functions that are differentiable on an open interval a to b containing c, except for possibly c itself, which again, it's an indeterminate form. You could get 0, or you could get an undefined. If the limit of f of x over g of x as x approaches c produces an indeterminate form 0 over 0, then the limit as x approaches c of f of x over g of x is equal to the limit as x approaches c of f prime of x over g prime of x, meaning that if you take the derivative of the numerator and the derivative of the denominator and then find the limit of that particular ratio, it will be the same limit as the original limit, okay, provided that that left or right limit exists. And this result also applies if the limit of f of x over g of x approached any of the other following indeterminate forms. And I get infinity over infinity, negative infinity over infinity, infinity over negative infinity, and negative infinity over negative infinity. And then lastly, L'Hopital's rule can be applied more than once to remove an indeterminate form. So quite literally, if you do the derivative first and you still get an indeterminate form, it is possible to do L'Hopital's rule again and again and again until you get a form that you can find the derivative of. Okay, so two quick examples. Let's first look at the original one that I had up there. We saw that this limit ended up going to 0 over 0. And so what we want to say is that this limit here is going to be equal to the limit as x goes to 0. Remember, we're going to 0 of the derivative of the top. All right, so let's go review our derivative rules. So the derivative of e to the u is e to the u times the u. So that'll be e to the 2x times the derivative of 2x, which is 2. And then the derivative of any constant is 0, so we're going to leave that alone. And the derivative of x is just 1. So this limit, as x goes to 0, well, just like in the last one, e to the 2 times 0 would be e to the 0, which is 1. 1 times 2 is 2. 2 over 1 is just 2. And so that limit is fairly easily evaluated once we use the L'Hopital's rule. All right, and then I had one more example. I thought I had written it down, but guess not. So this is number 36 from the book, and so it is the limit as x goes to infinity this time. I thought I'd do an infinity one. The limit, or no, excuse me, it's not. I already done the limit. It's the ln. It's the ln of x to the fourth over x to the third. Now, as x goes to infinity, clearly the ln of x to the fourth is going to go to infinity. Remember, just real quick, the ln function looks like this, and it's going to go to infinity. And then when I raise x to the fourth first, that thing's going to get bigger even faster, making this ln go up fast. So again, and then on the bottom, x to the third, obviously, as x goes to infinity, this is also going to go to infinity. So that's why I have an indeterminate form in this particular case. So let's say this thing, again, the limit as x goes to infinity. And I want to point out, once again, don't be lazy here. Do not stop writing the limit until you evaluate the limit. All right, so make sure you have it at each space until you actually evaluate the limit or find a place where you can evaluate the limit. So let's take the derivative of this. So remember, the ln of u, if I'm going to take the derivative of that thing, d over dx, is just going to be 1 over u times du over dx. So in this particular instance, that limit is going to be 1 over x to the fourth times the derivative of that, which is 4x to the third. And then the derivative of x to the third is 3x squared. And so let's simplify a little bit before we can take that. So I get the limit as x goes to infinity. Well, I get 3 of the x to the third and x to the fourth. 3 of the x's cancel out, and I still have a 4 on top. So it'll be 4 over x all over 3x squared. And so I've got this fraction x, or 4 over x, divided by the fraction 3x squared all over 1. So I'm going to flip my bottom, make the reciprocal of the bottom fraction, and then multiply. So I'll have the limit as x goes to infinity of 4 over x times 1 over 3x squared, which will be equal to the limit as x goes to infinity of 4 over 3x to the third. Now, this is no longer an indeterminate form. We have a method for doing it. It's kind of like the method that we used to solve this first one up here, where we compared the degrees of the numerator and the denominator. This is a ratio of two polynomial functions, the polynomial function 4 and 3x to the third. And so since the degree of the numerator is less than the degree of the denominator, this thing goes to 0. So it's one of those rules that we had before. So there's our limit. And we can have a 0 limit. All right, folks, that is the gist of it, and that is the last one that I've got. So here is your last Star Wars fun fact of the day. These three are very famous actors. I'm hoping that even though y'all are young, you have at least heard of Kurt Russell, Christopher Walken, and Al Pacino. And way back in 1976, these guys all tried out for the part of Han Solo, which eventually went to the now famous Harrison Ford. Well, that's all I got for today, folks. It's a pretty short one, only 10 minutes long. Holy cow, I'm either getting good or this is easy stuff. So I will see you in class. Goodbye.